Hi everyone, welcome back. Today we'll have Benedict speaking on Atiyah Bott.
Okay, so what Atiyah Bott does is it analyzes the moduli space of G-bundles by infinite dimensional symplectic reduction, and one of the key results is it calculates the cohomology of the essentially the coarse moduli space, or equivalently the moduli spatial stack of equivariant. Moduli spatial stack of semistable G-bundles. So the first point, so what I really want to do today, first thing I want to describe how we can describe this moduli problem in terms of infinite dimensional symplectic reduction of gauge theory. And then secondly, I want to talk about how there's really a sort of string of results about finite dimensional group actions such that the infinite dimensional analogues of them are really what Atiyah and Bott use. So far, we've been working in the complex algebraic world. And in the complex algebraic setting, we had that X, we have some G-bundle X with a G action such that to tell locally it's a trivial G torso. Now, we can suddenly give this definition in the category of complex manifold. So P is subcomplex manifold, X is subcomplex manifold, GX on fibers, and it's locally trivial, where here we can just use the classical topology rather than. So that there's a get format from, so in the complex of 4 G-bundles where both of these are complex algebraic manifolds, and this is a map of complex algebraic manifolds. We're going to call these ones holomorphic principal bundles. Now, you have a forgetful map to principal bundles in the G-bundles in the C infinity. So, namely, I could have P and X as above, but this time I only require that these are smooth manifolds. Now, what we want to do is we want to describe the holomorphic G-bundles in terms of extra structure that we can put on these principal bundles. So I'm going to do this in the case of vector bundles, and so we have our differential operator E maps to E tensor omega 1x, where this is the C infinity differential one forms. And we can split this into the part that we can split this into holomorphic one forms and anti-holomorphic one forms to give and now, if it's the case that your bundle is actually holomorphic, we have that del bar squared is equal to 0. and del bar satisfies Leibniz. Okay, so what we're going to say, we're going to call such an operator a low-volt operator. And the idea is that if E mapping to X if X is a complex vector bundle, what this means is basically the bundle is living in the C infinity world. So the transition functions are C infinity functions going to GLN rather than holomorphic functions. It is not, E is not put with a complex. But the proposition is that if we have a complex structure and del bar E to E times omega what one C infinity is a low-volt operator. Then there is a holomorphic vector bundle underlying E, with respect to which I really should do the sheet section. Then there is a choice of complex structure on E with respect to which the map E to X is a map of complex manifolds. And as such, you actually have a holomorphic vector bundle. Such that we recover delta. And essentially, all you have to do here is you have to find coordinates which are holomorphic. And you can do this by, if you pick a trivialization, I can use the top of this board, right?
Oh yeah, no, in fact, I'll let you know. Yeah. The main factor, so right there, yeah, start there, perfect.
E restricted to U is isomorphic to U cross Cn, this is like C infinity amplification. We then have that I'm going to write this. So in this case, you can see, take the functions and we actually have a debug, which corresponds to, the part of the differential with anti-holomorphic parts. And we can write this as this plus some wonderful. And then all we need to do is we need to pick coordinates such that del bar E annihilates the anti-holomorphic coordinates. And it turns out that we can do this by coordinates of 1 n coordinates C1, Cn. So we have the dzi and we have the dw plus omega ij w wj. And if you work out, these will actually give you holomorphic coordinates such that if you take the d bar, you recover del bar e. And this is just a calculation. But the point of this is that this changes how we should think about this gives us a new way to describe the classification of holomorphic G-bundles on some complex matrix. So the new moduli problem is you want pairs of e to x a smooth vector bundle. Smooth complex vector bundle. Or equivalently a G-bundle in C infinity boundary. And del bar epsilon to epsilon and omega bar x, a double operator. And in general, you have the same good columns. Adjoint bundle. So the first thing to realize is that this space of operators is infinite dimensional because we're using C infinity operators. So the natural question is, when do two double operators give us the same holomorphic vector bundle? And the answer is that it's when the group of symmetries of the C infinity G-bundle will take one connection to the next. So we have omega C infinity of x of add A. So add A is equal to E cross G, or equivalently is equal to automorphisms of A, where this G is the automorphisms of a particular type. So, and the reason for this is if I have G in quantity, I can apply that automorphism, and I will go from one Debolt operator to the next Debolt operator. And this symmetry tells you that there's an isomorphism of the pairs of a smooth complex vector bundle and the Debolt operator. So, and conversely, if I have E1 and E2 are isomorphic, well, firstly, we can use that to rewrite the E2 as E1. So we can see this as E1 del E2, right? And then there must be some automorphism of the vector bundle or G bundle E1 that takes the Debord form to the other Debord form. So that is to say, there is some G in. Sorry, why did I write a mega snippet? I meant to write it down. Comes the infinity of beta set E, taking del E1 to del E2. So our problem can now be written as a quotient. We can say what we really want is to consider based on Debord operators. Modulo modulo G. So this is some infinite dimensional space quotiented by an infinite dimensional group. One of the difficulties of doing it as such is that the space of Debord operators is slightly hard to describe. So the trick is that one can rewrite Debord operators in terms of unitary flat connections. So I'm just going to do the vector bundle case. So firstly, if E to X is a smooth vector bundle, there exists a Hermitian form. So that's the section. Yeah. Okay. Each ends of the bus. Okay. Now, given the Hermitian form, we can rewrite the Debord operators in terms of unitary connections. So if the one of X is a Hermitian form, a unitary connection is such that d of epsilon nu is equal to d epsilon nu plus epsilon d nu for all sections epsilon nu. But equivalently, what you should think about it as is if we have unitary, we have an idea. If we think about C, on C, a Hermitian metric is Z comma W mapped to Z bar W, sorry, Z bar times W. So in particular, Z is equal to normal length of Z squared. So what this says is you have a notion of circle of a given radius inside each fiber. If you have a one-dimensional, if you have a Hermitian line bundle. And if you have a Hermitian vector bundle, you have a notion of the sphere of a given radius. Complex space. Then a result from differential geometry is that given E, comma, a Hermitian form, there is an isomorphism between the Bolt operators and unitary connection and unitary connection. And the map in this way is that I can write D again as D prime plus D double prime, breaking it up into a holomorphic and an omega naught 1 and omega 1 naught part. And I map to D double prime. I don't think I want to talk about the differential geometry. What I want to instead talk about is if we just think about the line bundle case again, the symmetry is of C, you have GL1, C star. Now the symmetries that preserve the Hermitian structure, they have to preserve the circles of a given norm. So it has to be the unitary group U1. So what this means is that unitary connections are equivalent to connections for the real, compact real form UN of GLA. You know, UN associated UN. And here, in general, we replace UN with the compact real. So I assume the torus is. Okay. Now, this is easily describable. This is just symplectic section of P, C infinity section of X of this is a gamma X at A at minus 5. And that's because if you take any two connections, they differ by a 1 form. So, sorry, I should add a, it's a X. No, and at this point, I can go back to. At this point, any two connections actually differ by a Lie algebra value 1 form. And so I have it actually have that this is a atom bag model of this. Okay, and this is easier to work with than the space of Dolbolt operators. And also, this is a symplectic space. So the tangent space is just identified with the space of one form. So if I have two one forms, well, I can take the integral over x of alpha going to beta, and I should take the trace of this. So this is my symplectic. Okay, so then the next part is, how does the group act? And I'm only going to remember how the real part of the group acts. And that's that we have add P embeds into add E. So automorphisms of P scale up to an automorphism of the complex vector bundle E. And well, add P will just act on the connections by pulling back the connection under the automorphism of the real bundle. And so connection. Okay, so what's the large scale structure? The large scale structure is that we have both operators modulo G. This is isomorphic to UN connection. UN connections P mod G. And we know how a real form of this group acts. The R inside J so the finite dimensional analogues that we should be thinking of is as follows. I have G acting on some space M. Here, G is, let's say, algebraic, and M is, in fact, projective, and hence K. Inside G acting on M, I have K, the compact real form, acting on M by symplectic morphisms. And what I want to do is I want to describe some notion of the quotient of M mod G. And I want to describe it in particular by thinking about the action of K on M with its symplectic structure.
So that's just restricting the action of G to K. That's an inclusion on the left.
Yes.
It's not K's acting on G. Okay.
Yeah. So we should be slightly careful because Excel wanted this to act by symplectic morphism. So to do that, we need to have some property of the structure of G acting on M. And that is that, well, the projective structure corresponds to a line bundle. The projective structure corresponds to L on M. We need there to be a G equivariant structure on the line bundle L. G acting on A. Okay. And that means that the symplectic structure obtained from the projective structure obtained from this line bundle will indeed be K equivariant. Okay. So somehow we've thought about static quotient here by constructing the quotient stack. What we really want is we want a quotient that is some actual scheme which approximates the static quotient as well as possible. So if G acts freely, we want the quotient space. If G doesn't act freely, we want the best we can do. So one answer to this is we could try to say, okay, if M is affine, so yeah, I know I'm swapping between projective and affine, we'll come back to it. Then I could take the spectrum of G equivariant functions on M. And this will be some space. The inclusion from KMG into KM gives me a map from M to this space here, which is called the GIT quotient. Okay, and this is some approximation to describing the G orbits on M. It's a consequence of a theorem of Haboush. Points correspond to closed orbits. Now, informally, it's in some ways clear that we have a map from this space to this space. And the reason is that if I have some open orbit, we have to have that G invariant functions a constant on the closure of that orbit. So if I was an orbit, and what this means is you can sort of see what the different G orbits are going to get squashed together into the points of M mod mod G. In particular, if one orbit is in the closure of some open orbit, they have to map to the same point. And then the result, and then every, so this is really a theorem, every orbit O has, there is a, for every orbit O, there is a unique orbit with a unique closed orbit in O. And essentially what the map from M to M mod mod G does is you take your orbit, you go to the unique closed orbit in the closure, you map to the corresponding K point. Now, I haven't demonstrated this because there's something very non-obvious here, which is that if I take two different closed orbits, we need to find a function that separates the two. So first with this, finding. close. Okay, now I want to come back to the projective case. So rather than functions, I should think about sections of the line bundle L on M. If alpha down, current, and define, we're going to take R is equal to sum of sections in L tens a D. This gives me a projective algebra, and we can define the GIT quotient, depending on L, as proj of RG. Proj of the G invariant function R. The one thing to note is that we can do this in both the projective and the affine case. In the affine case, because R naught is just invariant functions on X, M. Okay, we have a map M mod mod LG mapping to M mod mod G, which is prime. In the projective case, you need the equivariant line bundle to do this. Mod mod G is a point, so it's true. Well, it's still true, but it's not helpful. Okay. In this case, where we have the equivariant line bundle, we're not necessarily going to get a map M to M mod mod G because of the existence of base points. So what you have instead is you have M removed base points so M mod mod LG. We call these unstable points. And these things. Perhaps a natural example is if I take GM at .HO by scalar, and then if I just take the naive quotient, I'm just going to get the point because there's one closed orbit corresponding to 0. If I do, if I take L to HO, which I can get L corresponding to a character, GM to GM, describing how do you actually find it. And in this case, HO mod mod I is P1 because we remove the unstable point at 0 and you just get projective space. And in fact, you really just get proj of you get the definition of projective space. You get proj of the usual algebra. And we can say that, and again, an analog of this theorem is that points of M mod mod L C correspond to orbits that are closed in the semi-stable locus.
So just as a quick sanity check, if we have this L, the sample line bundle over M, That's just giving us projective structure on M. So this M mod mod G is going to be a refinement of M. It doesn't involve like the total space and line bundle in any way. It's just what we're thinking of it as a kind of quotient on the projective variety that M is when the projective structure is given by L. Is that my understanding?
Yeah, on the part of M that is given by a projective variety, yes. M complement unstable pockets.
Okay, yes.
And then, yeah, we're amalgamating orbits, but we're amalgamating the subset of orbits that come from the semistable point.
And that's always and this mod LG is actually comes with the removal of the base of the bad points, or
yeah, I mean it does that for free.
It does that for free. Okay, brilliant. Okay, so I do understand. Okay,
I mean what you need to be non-unstable is you need to have there to be a section that's non-zero.
Yep. Perfect. So yeah, this LG doesn't mean total space alignment. It still is living under M.
It was living under M.
Under N minus some points. Under N minus some points.
Yeah.
Sorry. Thanks so much.
Okay. So at this point, I want to change and I want to say, can we recover these quotients M mod mod J in terms of the action of the compact group K inside J? So the idea here is that, well, we can, provided the action of K is Hamiltonian, because there we have a reduction. So the first thing to ask, what's the dimension of this quotient? Roughly speaking, if it acts freely, you're subtracting 2 times the dimension of G. So that's, no. You're subtracting the dimension of, if G acts freely, the complex dimension of M mod mod J is equal to dim C M minus dim C J. Now, this means that when we're considering K acting on M, here K is real. And so if we just took, if K acted freely, this would be of dimension, real dimension, 2 dim C M minus dim C J, which is dim R of K. So if we're going to somehow relate M mod K to M mod mod J, we need to remove more dimensions. Such a theory is given by the theory of Hamiltonian reduction. Okay. So if we have K act on M omega by symplectic morphisms, then if I have some element of the Lie algebra of K, that gives me a vector field on M by the infinitesimal action. Psi vector field. Okay, now from that I can get a one form by pairing it with omega. If this one form is exact, then I can get actual functions by picking a function that differentiates to this one form. action is Hamiltonian if there is a map from G to the functions on C infinity of M, where we realize this as a Lie algebra under the Poisson bracket. Okay, something that's to HSI such that D of HSI is equal to omega of these like that. And given this, we can define a moment map such that D of HSI is equal to omega of psi. Or perhaps another way to see it, that M is telling you what the infinitesimal action is. The action is specified here by this one form, and then we're seeing it as a derivative of this function, where we then pair with xi, where xi is an element in the Lie algebra, which corresponds to a tangent vector field.
So it is 450, so feel free to work out when's best for you to
right. Let me go a bit longer. And this can be shown. So there's some options with respect to normalization of this, but we can make this make this K equivariant for the coordinate action on the okay. I want to give two theorems which can then be used, which we then want the infinite dimensional versions of them are used in Atiyah Bott to prove that, to prove two things, which I'll okay. So the first one is the big picture of where we're going. In good circumstances, the symplectic quotient is defined as mu inverse of 0 mod k. And here, at least if k acts smoothly, we've reduced by 2 times, the real dimension we've dropped is 2 times the dimension of k. Firstly, by imposing this equation, and secondly, by quotienting by k. So when I say quotient by k, I'm just going to assume they act freely for the moment. Okay, so at this point, we now have two quotients that we can compare. The Kempf Ness Theorem says, in both cases, we have that mu inverse 0 of k is isomorphic to M mod LG, where L is the line bundle that gave us the relevant symplectic form on M. And in the Atiyah Bott case, mu inverse of 0 is, okay, if E is topologically trivial, then mu inverse of 0 is the space of flat connections on E. Flat connections on E. And if you push this a bit harder following the work of Donaldson, what this gives you is a diffeomorphism This is the theorem of Narasimhan boundary, which was reproved via this method by Donaldson, that there is a diffeomorphism between the space moduli of semistable topologically trivial G-bundles X and the moduli of irreducible representations of pi1 of X to the compact real form of G. And essentially the idea is, well, okay, we move from flat connections to representations by taking the monodromic. Then you can define good quotients on either side by taking, on this side, you're taking mu inverse 0 mod k, but you're taking a certain subset where k acts sufficiently well that you can actually quotient by k. And K is the space of automorphisms of the real bundle. On the other hand, on this side, you have the you have this quotient where this is the space of all default operators, or equivalently all connections. And this is the quotient by the complex gauge transformation. So the first thing you recover is that, Narasimhan, Chaudhry, and Donaldson. The second theorem that I want to talk about is a theorem, well, there's a stratification due to Irwin, Kempf, Hesselink, and someone whose name begins with N. Ness. Okay, so
HKKN.
HKKN. And essentially what you do here is you take M, you map by mu to K, then you take the norm on K to R, and under good circumstances, this is a perfect Morse function. Which means that you can, you get the Morse decomposition. And you get a description of the cohomology of M in terms of the cohomology of the strata. And you can also do this for various equivariant cohomologies if you have an equivariant Morse function. So what you want to do in the Atiyah Bott case is you'd like to think about the G equivariant cohomology. So this in our modern language will be the cohomology of moduli stack. This will be equal to a direct sum of equivariant cohomologies of strata. What are these strata? These are the HN stratification strata that Griffin described last time. Harder Narasimhan. Or rather, this is the analogue of the HN stratification inside the space of connection. Now, Atiyah Bott don't quite do this. There's analytic difficulties to showing that it's actually a Morse function, as you need to show that the critical loci are all first order. But essentially what Atiyah Bott do is they say, okay, these ought to be naively the strata, and then they prove by a different method that you got, they prove directly by the Tungeson spectral sequence that, or exact sequence that you've got such a decomposition. So that's where we're going. What we want to do, what we still want to do, is we want to describe how Kempf Ness is proved. We want to describe this statement, and we want to then describe the analogues in the Atiyah Bott setting, as well as describe the topological classification of C-infinity principal bundles, which we needed initially.
Right.
Okay, so I'm going to take a break and
Yeah. Turn it 5:10.
Yeah, absolutely. Thanks so much.
Okay. So I want to start by returning to the Kempf Ness Theorem, writing this carefully, and writing how one does it in the infinite dimensional set. So the careful statement of Kempf Ness . Okay, so okay, G, again, it's complexification. We take X, subset of some projective space, projective variety. We're going to need a K-invariant dimension structure. X will equal once again M to the K star on the map associated to the symplectic form coming from this projective structure. So the Fubini to the And V inverse of 0 is in every polystable type. And this gives us both of them. With symplectic quotient, which is the error of K. And on the GIT side, we're using the line bundle, which is the pullback canonical of O1 on PFN. It's the one that gives you its projected structure. We should probably assume K acts freely to not be technical. Okay, so the polystable points is the subset of M semistable of points that lie on closed orbit. Okay, so at this point, we can see what we need to do. We need to show that as the K points of this correspond to the G orbits of the polystable points. So what we need to do is we need to show every closed G orbit, intersects B inverse of 0, and if the G orbit intersects B inverse of 0 at multiple places, those places are related by the action of the compact group K rather than of the complex group G. Closed, semistable, G orbit, intersects. So if a closed plus we made any orbit intersecting the inverse of 0 closed. And finally, we need that if O, a G orbit, if we look at O intersect closed, take O intersect B inverse 0, we need this to be a single K orbit rather than multiple K orbits. The strategy of this proof is as follows. What we do is we define the Kempf Ness function enter such that this is 0 on phi inverse of 0. this is K invariant and such that this is convex. With minima on the inverse of self. Okay, so what do we do at this point? What we do is we basically look at the flow along the Kempf Ness function. And we look at the flow within a given orbit. And we want to show that if that orbit, there's a unique minimum in the closure of that orbit. And how we do that is we just take a minimizing sequence, which is special in certain ways, and show that it has a limit. And well, and then if that orbit is closed, that limit has to be inside that orbit. And then that, and then when you're inside that orbit, well, that is your intersection with the inverse of zero. Some more details.
Sorry, can you repeat the third thing we need, please?
So the third thing we need is that a priori, a single G, what we could have is we could have the inverse of zero, and we could have this is O, our closed G orbit, and it intersects at 2 points. Parent K. Then a priori, those 2 points may not be related by some element inside K. What we want is okay, if you have 2 points here, these are related by something in K, and so we actually have a single K orbit. This not make sense.
We're doing it live.
No, we're going to cast a veil. But what I'm going to say is that, roughly speaking, if you take the orbit, roughly speaking, you have a surjective map, K cross Lie K, G. And this is, you just want to take here K, K by to a X of xi. And what this means is if you think about how the G action acts, K is going to act on fibers of the moment map because it's K equivariant, while this part, K, will tell you how you move around between fibers. And the idea is then that on a given orbit, you have this, your K invariant function really comes down to specifying a function on the Lie algebra of K. The function is going to be convex on the Lie algebra of K, which means that there's really going to be a minimizing point or some set of minimizing points. And then we can just act by those elements, or rather their imaginary exponentials, to move us to the central function. Okay, this, as I say, these notes do not on retrospect make sense. So that is all I'm going to say. And yeah, if you want to sequence, if you have some point x, m, then m polystable, what we'll get is we'll get a sequence of xi I such that x of I xi of m converges to a point in B inverse of 0.
X I xi I.
Yes. Okay, that's that.
J.
And essentially, this is how the proof of part of it works, at least. Once you have this converging sequence, then you have an intersection with B inverse 0 of the closure of your orbit. And then if the orbit is closed, which it is if you're in the polystable locus, that actually gives you an intersection of your orbit with the 0 fiber of the moment. Okay, and as I said, my notes on there were errors. That is all I'm going to say.
So the conclusion of Kempf Ness is a description of the GIT quotient for a symplectic.
It's a description of the GIT quotient as a symplectic quotient under certain conditions.
I see.
And why this is important is because in the Atiyah Bott setting, we know that there is this symplectic action of the automorphisms of the real form of the bundle, and that has a symplectic action on all connections for that bundle. Now, this is a symplectic action, and so we can use the moment map here to get one description of the space, and the space should, if one can prove an analog of the Kempf Ness theorem in the infinite dimensional setting, be equivalent to giving the quotient of all connections by G, which is equivalent to the quotient of all de Bolt operators by G. So this is actually one of the points where Atiyah Bott is harder, because here you're doing the convergence of a sequence of functions. And infinite dimensions is always annoying. Okay. What I think I want to say now is what part is it there? Okay, I think I want to say just So this was talking about what we wanted to do the analog of in the symplectic setting. So what I should say is roughly what some of the extra pieces that we didn't state were in the symplectic setting, and how this, gives us the two results. So, but firstly, and I feel we're going to run out of time on this, we need to, our description of G-bundles was as a C infinity G-bundle plus a Labol operator. And we still have to look at what the C infinity G-bundles are classified by. Okay. So in case of G equals GLN, then the C infinity GLN bundles are simply classified by degree. And if E is a vector bundle, you can take the degree of the determinant. More generally, the C infinity G-bundles with here I mean isomorphism plus thereof are classified by the fundamental group G. Okay. So we know that, so firstly, there's two approaches to this that we can use. One is using a topological approach of what Noah will be talking about next week with uniformization. But instead, I'm going to be talking about what we want is we want to consider topological maps to a PG, but this is a topological classifying space. So the first thing to notice is that this is equal to its own two scalars. And as such, this space of topological map is equal to the three skeleton of BG.
Sorry, X is now the Riemann surface.
X is now a Riemann surface, yes. So it's more complicated in general. Okay. Okay, so we also have, so what we want to know is we want to know pi naught of BG, pi 1 of BG, and pi 2 of BG. We know that pi naught of BG is equal to and find the other homotopic groups, we can use the vibration here, and we can use that EG is contractible. To work out the homotopic groups of BG in terms of homotopic groups of G. So sequence we have is so this tells us that the homotopy groups of Bj are the homotopy groups of G shifted by 1. Okay. So that tells you that we're assuming that G is connected. That tells me that I naught of Bj is equal to a point. I1 of Bj is equal to I naught of J is equal to a point. And I2 of Bj is equal to I1 of J. So now then that means that after we take the 3 skeleton of Bj, this is isomorphic to K I1 J2, where this is the Eilenberg-MacLane space by definition. And this represents cohomology with coefficients in pi1 of J. That means that 3 is equal to x J, which by the universal coefficient so this gives us that we have this discrete set parameterizing the top. Then for each topological bundle, we're going to have this infinite dimensional quotient describing that part of the moduli space. So in order to fit this into the story about symplectic quotients that I gave before, I need to specify what the moment map is. And I need to say what the analog of the Kempf Ness functional and the analog of the functionals involved in giving what should be a perfect Morse function. Okay. So the moment now. So firstly, the moment map is mu of a so this is a connection on a principle. So also at this point, note pi1 of J is equal to pi1 of the compact form. So we can actually take a compact form, and this is canonical topologically. So we look at the connections on a principal G compact bundle of a fixed topological. Okay. P mapping to, well, it needs to map to Lie K star, where that is gamma, the infinity of x at P, which we can identify by Poincare duality with two points. So what we're going to do is we're going to take the curvature. If the bundle is trivial, if the bundle is not trivial, then you take the curvature and you subtract a constant. And what this constant is basically you don't have any flat connection on a non-trivial, topologically non-trivial G-bundle. There's a topological obstruction to both. But what you can have is you can have connections with constant curvature. And what you do is you subtract the constant curvature part to basically just get something that looks very much like the normal, the topologically trivial case. Do is take connection D. E maps to FD curvature minus a constant section of Z P of G inside at N. And this constant section is such that what is this constant section? This is the curvature of a connection with constant curvature on the bundle thing. And this is sort of one way of seeing this. Is another way to do the classification of pi naught is to use the Chern class of your G bundle. If you do the Chern class, you can see that as an integration of curvature over your manifold. So if it's constant curvature, it has to be fixed. Okay. So this is N by 2 x at P, as we said before, it's isomorphic. Okay. And indicate, so we recall that curvature is just sections of A, the sections of A on A1, then you can do it again to get on A2. And this is curvature. And if you believe me that this is the moment map, then it tells you immediately that U inverse 0 is equivalent to connections with both bundles with a connection of constant curvature. And if you just believe that the Kempf Ness theorem should still be true in this infinite dimensional setting, which is perhaps a bit of a reach, what will it say? Well, if K acted freely, well, let's say sufficiently nicely, it would say that mu inverse of 0 mod K, where somehow K is sufficiently nice that we can make sense of this. Sorry. So K is what of K. This would be isomorphic to diffeomorphic. To all Bott operators modulo Bott of the complexification of the bundle P. Now, the reason that this doesn't quite work is that neither side of these is well behaved enough to have some sort of coarse quotient. And the answer is that essentially you have to take semi-stable points on both sides. And on this side, you have to take the ones that correspond to irreducible representation. Definitely. Can say that zero irreducible. This means that the associated universe of 0 irreducible, so irreducible reps of an extension of pi1, which is isomorphic by reinterpret to by reinterpret to vectors of constant curvature. Modulo what the modulo and the point is that this will be connections of constant curvature quotiented by warps P, where connections I have to, because I've said irreducible here, I have to say semi-stable. These don't include. It's diffeomorphic. So on the other side, we're going to have semi-stable G-bundles. Modulo and so semi-stable G-bundles are given. So topological classification here corresponds to the extension here, which corresponds to the actual curvature here. And you have to fix one for the actual group digression to make sense. And this there is a theorem of Narasimhan structures. And then the new proof that was proved by Donaldson using this approach. And from the point of view of our point of view, you should think about this as the coarse moduli space of BunG tau, where tau is the topological class of the G-bundle. Okay.
So that's semistable G-bundles of what?
Of a given topological class. Because we have to take a union over all topological classes to get all G-bundles by this approach. We have a different symplectic quotient for each given topological class. Okay. I am just going to say very rapidly that the next part is that the candidate for a perfect Morse function that gives the HKKN stratification is the Yang-Mills function. And here I take a connection. Connection. Let's take this definition. Connection E, and then I map it to I want to integrate over X. I want to take the norm of the curvature. Curvature does indeed have a norm because I'm working with a Hermitian metric. And the reason this is called the Yang-Mills function is that we're meant to use the critical loci of this and things that flow downwards to critical loci to understand cohomology. So the downflows to the critical loci are the Nelson and
So what was the subscript on that? It says curvature on D on the other side.
Yes.
That's yes, that is match I curvature on D. What's the that? What underneath the D on the other side of the arrow?
D is we're seeing it as the Hermitian connection on A.
Hermitian connection, sorry.
We get downflows to critical loci is equal to HKKN strata. Or if we so you have your Harder Narasimhan parabolic is a specified parabolic. And the critical loci, the equation for the critical loci are equal to the Euler-Lagrange equations for this functional, which are equal to the Yang-Mills functions. And finally, there's an argument inside Atiyah Bott that this should be the case, but they can't show that this is actually a perfect Morse function. And as such, what does that mean? So that means that, well, but you still have the stratification. It's the Harder Narasimhan filtration. You can just directly prove the Harder Narasimhan filtration. If you take the sum of cohomologies of that, equivariant cohomologies of that, you get the equivariant cohomology of the entire space of connection, which is the cohomology of the stack BunG. And the stack BunG is sort of easy to calculate the cohomology of. So Atiyah and Bott do the reverse, and they use that stratification to calculate the cohomology of the semistable. Okay, and I'm going to finish it.
Are there any questions? Maybe just for the audience's sake, since we're discussing it midway through, are there good references you might recommend for the HKKN stuff, things like this?
Okay, yeah. So the best reference for the relationship between symplectic quotients and geometric quotients, there's two I really like. One is the final chapter of Mumford-Fugate-Cohen's geometric invariant theory. The other one is Woodward's notes on GIT and symplectic quotients, which are very nice. Then sort of for GIT more generally, there's Mumford-Fugate-Cohen. There's the final section of Jared Alper's notes, stacks and moduli. For cohomology particularly, Cohen has written a short note on cohomology of symplectic and GIT quotients. And there's also a very nice set of notes by Richard Thomas on geometric invariant theory. And this infinite dimensional stuff, so Atiyah Bott, I think, really started it, and also Donaldson's proof of the Narasimhan theorem, but now it's everywhere.
Any other questions? Comments? Thank you, speaker. I guess we can go out to dinner.